My name is Khushi. I lead research at a company called Predicate. For some more introduction to myself, before this I used to work at a VC firm where we focus on applied cryptography called geometry, and then before that I was in school. So I'm going to talk a little bit about Predicate, what it is, why we built it, the components in the architecture, one of our use cases with Aleo, which is the first integration we have going live, and then some new research that we're thinking about, which is risk management for AI agents. And that is absolutely a clickbait title, so hopefully it'll be interesting. Cool, so why we built Predicate. Main reason was looking to Web 2 companies. Most of them needed some kind of rules and conditions on their users in order to scale. And so let me explain what that means. Basically, if you look at PayPal, they had to build this extremely comprehensive and complex anti-fraud engine entirely in-house in order to ensure that all users and transactions on the platform were not fraudulent. Similarly, Uber has reputation systems that I'm sure we're all familiar with, both on the rider and the driver side, in order to make sure that all entities on the application are adhering to the rules that they said that they would when they joined. And so if you zoom out and look at what that actually means, they're essentially like prerequisites to interacting with the platform. And so what we do is something very similar for smart contracts. We basically allow you to create prerequisites for users before they can interact with your smart contract. And so how does that work? Well, the smallest unit of work in our system is a predicate, hence where our name comes from. It's a predicate function, which is basically just a function that returns a true or false result. An example of what a predicate function could be is something like checking if a wallet address has stolen funds in it. And so what that could be indicative of is maybe this wallet address was used to conduct an exploit, for example, and now they have these stolen funds, and they might want to launder them through an application. You can take this predicate and turn it into a rule, which is basically you attach some action to the outcome of that predicate function. So if the predicate function says, yes, this wallet address has stolen funds in it, maybe you don't want it to interact with your application because you don't want to facilitate money laundering. Then the final part is a policy. And so all of these rules can be stacked and combined to create these things called policies, and policies are specific to your application. So you can decide what kind of risk management stack you want for your application, and it contains all of the rules and constraints on how users, what types of users and how users can interact with your platform. So how does the system actually interact with an application? Well, a user will interact with some client interface. I'll take Aleo, for example. They're a layer 1 blockchain, and they integrate Predicate in all of their bridges. So when a user goes to bridge funds from Ethereum to Aleo, for example, then they will send that transaction details to the Predicate network, which is a system of operators. Those operators check to see if the transaction details adhere to the policy that Aleo had set out. And if they do, they return true, and they return the signatures of the operators in the network. Then the transaction is sent to the smart contract on-chain with the operator's signatures, and those signatures are verified using the predicate verifier, so that you can't bypass it by interacting with the smart contract directly. If you go in a little deeper, the actual network consists of a few different components. So there's the predicate middleware, which takes the transaction information and broadcasts it to the operators. Then there's the operator network, which consists of currently a proof of authority network, eventually will be permissionless with rewards and slashing. And then they can also interact with external information providers, which is third parties like TRM, Hypernative, or Solidus. But what that does do is it does create a centralization component to your system. So that's something that people have to keep in mind when they're setting up this risk management stack for their application. So, example use case. Aleo is a privacy layer 1 blockchain, and so they knew that they would need to have a set of basically like rules and compliance best practices for all bridges on their platform. So they created a governance proposal, ARC 100, that governance voted on and passed, that consists of a series of rules. Some of these are things that you can do in the predicate network, and then some of them are things that are implemented in the bridge natively. So there's 24 to 72 hour delays, which is typically implemented by the bridge themselves. And then there's things like rate limiting, as well as OFAC sanction screenings, and guarding against like transactions from certain locations. That can all be done through the predicate network itself. So now for the clickbait. Research on risk management for AI agents. This is pretty interesting because I feel like AI agents pose a different problem when it comes to security than something like bots could do previously. And so this is something I totally stole from Twitter, but I thought it was a good description. An AI agent is a piece of code that can plan, decide, and act independently. But what makes it different from bots, right? There's three main components: reasoning and self-reflection, taking action, and planning. And that's actually really important because the taking action part can happen with both AI agents and with bots, because AI agents typically have access to a wallet or they have access to someone's Twitter account. Bots have the same thing where they have access to a wallet. Like if you use Banana Gun on Telegram, it'll have access to a wallet and it can conduct transactions through it. But the very interesting thing is that bots are typically coded with a very specific set of instructions and constraints. So it conducts transactions within the constraints that you have explicitly outlined for it, whereas AI agents have their own reasoning and self-reflection, and they can plan longer-term goals as opposed to just a single transaction within a specific price range. So it creates a whole new area of transactions that AI agents can do on-chain that you actually don't have control over. But why does that matter? Well, what the actual regulation and security is around AI agents is very unclear right now. So if you deploy an AI agent, that AI agent has a wallet and it does stuff with that wallet, no one knows who's actually responsible. It could be the AI agent, but that's a piece of code, and so typically it wouldn't be the AI agent, but it could actually be the person that deployed that code. And so you can use certain types of wallet structures like smart accounts or even multi-sig wallets in order to programmatically verify transactions based on a series of things like smart contract risk scores, compliance checks, whitelists, rate limits, transaction types, which is really interesting for us because this is stuff that we can already do with Predicate. And it's what we currently do at the smart contract level, but now you can actually do it at the wallet level itself. So when developers are creating AI agents that are autonomously getting money from random people on Twitter and then using it to shill tokens and then dump those tokens, you can set constraints around that. You can make it so that they can't do those specific actions, or they can't do things that dump on retail, or they do rate limits so that they can't drain the wallet that you just funded with hundreds of thousands of dollars. So it's pretty interesting. And it's not really just specific to AI agents, it's more around security best practices for wallets. Because a lot of the stuff that Sam talked about in his talk, for example, had to do with wallets getting drained, right? Well, if you have rate limits on your wallet, typically that actually prevents your wallet from getting drained because you can set daily limits, you can set per transaction limits. And so that type of wallet security just isn't very robust and doesn't exist today. But I think it can be something that becomes default in all wallets moving forward. So what would this look like? Well, in a smart account system, you can have conditional signing. So because you can program the conditions that allow transactions to be verified, you can require that you set a policy for your smart account that the AI agent is using. And before any transaction can actually be executed by that smart account, it has to go through a verification process through the Predicate network. This can also be something that's directly coded into the smart wallet. It doesn't have to use the Predicate network. It's just a more decentralized way of doing things. Similarly, you could do this with a multi-sig wallet where the AI agent has one signing key for that multi-sig, and the Predicate network or an automated signer of some kind has signing ability for another signature on that multi-sig wallet. There you'd need it to be 2 of 2 so that both signatures are necessary for that wallet. But using this, you can actually create a lot of security measures for wallets and make it programmable so you can change those security mechanisms whenever you want. So final thoughts, the reason why I said the AI agent thing was clickbait is because, again, it's really not limited to AI agents. It's just about wallet security. But I do think it's going to be one of the next things that we see a lot of development in on the wallet side, because we've seen user experience improve across wallets, but I think security still has a very long way to go. Cool, that's it.